Undetermined coefficients is a method to help us solve non-homogeneous differential equations. So our last topic was solving linear homogeneous differential equations with constant coefficients. That's going to kind of stay, but now we're going to look at the non-homogeneous variety. So looking at a straightforward differential equation, let's say we have y double prime plus 8y prime plus 15y. Now, what we saw last time was taking a look when it was homogeneous, equaling 0. Well, what do we do if it's not homogeneous and it was something like x plus 3? All right, well, for undetermined coefficients, here's what you're going to do. Always solve the homogeneous equation first. So basically we're going to ignore the non-homogeneous part and we're just going to look at y double prime plus 8y prime plus 15y equals 0. And then we'll get to the undetermined coefficients part. So let's go ahead and run through this real quick. We saw in the past, if it has constant coefficients, we can assume the solution is some exponential form. We take all the derivatives, plug it in, and again, I'm skipping a few steps here, because hopefully you've done a lot of these. This gets us to our characteristic equation, which this will factor m plus 3, m plus 5. So we get two solutions, which is what we were expecting. So our complementary solution, or the solution to the homogeneous part, should be c1e to the negative 3x plus c2e to the negative 5x. Nice and easy. Okay, now we're stuck with, well, if we plug that into our differential equation, we know that's going to give us 0. But now we got to find a function that if we plug it in there, we get x plus 3. That's the non-homogeneous part. To use the method of undetermined coefficients, the function on the other side, the non-homogeneous part, has to have repetitive derivatives. So to use the function has to have Okay, what do I mean by repetitive derivatives? It means when you start taking the derivatives, you eventually always get the same functions back out. Let's take a quick little side trip over here. If I had like x squared plus 3x plus 4. Well, by looking at this original function, what does this function, is it composed of? It's composed of x squared stuff, x stuff, and numbers. Well, if I take the derivative, I have 2x plus 3. The derivative contains x stuffs and numbers. I take the derivative of that, I get 2. That's just a number. And if I take the derivative of that, now and forever, I always get 0. So notice that it's repetitive because the function, the original function, and all of its derivatives contains a finite number of specific functions. What does it contain? X squared, x's in numbers all the way down. Something like sine 3x would also work. Because if you start taking the derivative of this, that would be 3 cosine 3x, negative 9 sine 3x, negative 27 cosine 3x. You see, no matter how many times you take the derivative here, what do you end up with? You either end up with a sine 3x or a cosine 3x. Of course, some constant multiple of them, just like here, some constant multiple of the pieces. So, as long as your function has repetitive derivatives, means the functions always repeat themselves, undetermined coefficients will work. Now, how do you figure out how to solve the non-homogeneous part? To solve the homogeneous part, guess what the answer will look like. All right, kind of what we did over here, right? We kind of guessed at this answer. Because of the form of differential equation, we reasoned out that the answer should be an exponential. Same kind of thing's going to happen here. We're going to take a guess at our solution. So our guess for the particular solution, remember that's y sub p, is going to be all the forms of the derivative of this function. So this is just a linear function. So if you look at this and all of its derivatives, what's the only things that are ever going to show up? Well, you're going to have some number times an x and a number. No matter how many times you take the derivatives of that, those are the only pieces that can show up. So my guess is going to be some number times x plus some number, right? That'll encapsulate the function and all its derivatives are all represented here. Now, before you call that a guess, that may not work. What you need now to do now is check to see if any of these terms show up in the complementary solution. Sometimes the guess will contain a piece that's already over here, right? If we had, or watch, if I guess some other number e to the negative 3x, let's say that ended up being one of my guesses. Well, since I already have that over here, I know that that can't generate anything except for a 0, because that's going to give me a 0, which means that would not be a good guess. And we'll see that in just a second what we have to do. All right, so if that's my guess, to find my answer, all I got to do is take all the derivatives, plug it in here, and figure out what a and b have to be equal to x plus 3. All right, so let's give it a shot. Yp prime would just be a, yp double prime is 0. So plugging that into the differential equation, plugging into the dE, I get 0 plus 8 times y prime plus 15 times ax plus b has to be equal to x plus 3. All right, from this stage, let's go ahead and clean this up just a little bit. I get 8a plus 15ax plus 15b is equal to x plus 3. Now you want to combine things based off of what they are. So here, notice this is a polynomial, so I have x terms, so I'm going to go 15ax, and then the 8a and 15b are numbers, so that's 8a plus 15b is equal to x plus 3. Now we're going to do what's called equating coefficients. If you take a look at the coefficients, for two things to be equal, the coefficients have to be the same. So the number in front of x on this side has to be the number in front of x on that side. So 15a has to be equal to 1. And the constant on this side has to be equal to the constant on the other side. Okay, so easy enough. We can solve this system of equations. We get a is equal to 1/15. If I substitute that in over there, that's 8/15 plus 15b is equal to 3. So 15b is equal to, let's scribble real quick, 3 minus 8/15, so 45/15 minus 8/15, that's what, 37/15. So 37/15. Divide both sides by 15 and we get 32nd, was that 225? Check my arithmetic on that, I think that's 225. Okay, so now we know what A and B are. So let's go back over here. I'm going to give myself a little bit more room. Let me get our done. So now we can actually figure out what our particular solution was. This was our particular solution. Now that we know what A and B are, it's going to be, what do we say? It was 1/15 x plus 37 over 255. Okay, so that's our particular solution. So the complete solution to this differential equation is, of course, the complementary plus the particular. So it's going to be c1 e to the negative 3x, c2 e to the negative 5x, plus 1/15 x plus 37 over 225. All right, so there's our solution. Now that we have the air quote complete solution, if you had any initial conditions, now's when you would apply them to try to figure out what C1 and C2 were. So anytime we're dealing with a non-homogeneous differential equation, we always solve the homogeneous first, kind of set that aside, and then determine what method we're going to use to go after the non-homogeneous part. If the function, where am I pointing? If the function over here has repetitive derivatives, we can just guess at a form of our derivative. So we guess, check to see if any of those terms show up in the homogeneous solution. If they don't, then we take all the derivatives, plug it in, and solve for the letters, the arbitrary letters that we put here. Now this ends up being a system of equations, can be messy sometimes. Just try to make your way through it. Once you have your complementary and particular solutions, the general solution is just that put together, and then apply any initial conditions that you might need to. All right, let's take a look at another example. Let's say if I have, I don't know, y double prime minus y prime plus 6y is equal to e to the 3x. Okay, this is a second order linear differential equation with constant coefficients, and this is non-homogeneous because it's equal to a function. So we always go after the homogeneous first. So when we go after the homogeneous first, I'm really going to solve y double prime minus y prime minus 6y is equal to 0. Again, this part, if you've been keeping up with the homework, should go really quick. By now, we assume e to the mx. When we plug it in, we get our characteristic equation, which this is m minus 3, m plus 2 equals 0. So we get two values for n, again, what we were expecting, negative 2, which gets us to our complementary solution. I'm just going to actually squeeze this down here in the bottom. So our complementary solution will be c1 e to the 3x, c2 e to the negative 2x. Now we're going to kind of put that to the side for a moment, and now go after the non-homogeneous solution. Okay. We really like to use undetermined coefficients because it really is a quick and easy method to do it. It actually can be a lot of work, but it is fairly easy to do most of the time. It's really just a lot of algebra. But to do that, I have to look at my non-homogeneous part and say, okay, does this function have repetitive derivatives? So does e to the 3x have repetitive derivatives? Yeah, no matter what you do, you're always going to end up with something times e to the 3x. So my guess will be something times e to the 3x. Now you got to check, does this piece appear anywhere over here? And it does. Our first piece is a number times e to the 3x. That's a number times e to the 3x. Now, we can actually figure out what we might have to do here. We saw when we were dealing with this method here, if we had a repeated solution, what ended up happening, we just ended up multiplying it by x when we applied our reduction of order formula that we gave you. So this guess won't work. But a good idea is, what happens if I take that guess and I multiply it by an x? Showed up in y sub c. So if your guess shows up in the complementary solution, what you need to do is take your entire guess and multiply it by an x. And then check again. Does this appear over here? If it does, multiply by x again until you get a piece that does not show up over here. Now this does not show up, so let's go ahead and take all the derivatives so we can plug it in. So yp prime, now we're going to have to use our product rule here. 3ax e to the 3x, and yp double prime is 3a e to the 3x, 3a e to the 3x, plus 9ax e to the 3x. Or if we simplify that, that's going to be 6a e to the 3x, 9ax e to the 3x. Okay, so there's all of our pieces. Let's go ahead and plug it into our differential equation and set it equal to the non-homogeneous side and see if we can figure out what all of our constants need to be. So according to our differential equation, y double prime, which is 6a e to the 3x, 9ax e to the 3x, minus y prime, a e to the 3x, plus 3a e to the 3x, minus 6 times a x e to the 3x has to be equal to e to the 3x. All right, let's go ahead and distribute everything out here and combine any like terms that we may end up with. 6a e to the 3x, 9ax e to the 3x, a e to the 3x minus 3a e to the 3x minus 6ax e to the 3x. All right, I feel like I'm missing okay, equals e to the 3x. Let's see what we got here. I need to check because I feel that something bad has happened. I'll show you how I know that. Missing 6ax. X. All right, let's see what happens here. That's right there. That's the. Oh, I missed an X. That's right. This is 3ax. Knew there was one wrong. I'll show you why I knew that there was a mistake there in a second. All right, when we go to combine our like terms, here we have a e to the 3x's. There we end up with 5a e to the 3x. And here we have x e to the 3x, x e to the 3x, and x e to the 3x. Now notice here, all of those end up canceling. That's how I knew that I made a copying mistake when I copied it over. Because I can't have those on this side if there's not any on the other side when they all have to have the same a. Right? So now it's really easy to see what a has to be. The number in front of e to the 3x on this side has to be the number in front of e to the x on that side. So a has to be equal to 1/5. See, if we would have had this, don't write this down. If we would have had something over here, something ax e to the 3x, but of course on the other side I don't have any of those over there. That means that a would have to also be 0 to make that go away. That can't happen, right? It can't be two different values in this case, it's only one. Okay, so now we know exactly what our particular solution is. Our particular solution was right here. 1/5 x e to the 3x. So our complete solution is c1 e to the 3x plus c2 e to the negative 2x plus 1/5 x e to the 3x. So this is our complementary solution plus our particular solution. It gives us the general solution to our differential equations. Now we still have two arbitrary constants in here. So if you're given any initial conditions, now is when you would apply them, once you have your complete solution. All right. Let's try maybe one more here. Let's make this one the hardest one yet. What if I have let's go x squared to 2x. All right, this one's going to be messy. Let's see if we can make our way through it. All right, so this is a second order linear differential equation with constant coefficients. This is non-homogeneous. We know we go after our homogeneous first, so 9y is equal to 0. I'm really going to shortcut this because hopefully, again, you've done the homework. Your complementary solution out of this is going to be C1 cosine 3x plus C2 sine 3x. So make sure that you can do the steps to get to there. All right, you put that to the side. And we're going to guess our particular solution has the form. Now, I'm looking at this. Does this have repetitive derivatives? Well, one way to look at it is I know x squared would have repetitive derivatives because all you'd ever get out of that is x squared, x's, and numbers. And I know e to the x has repetitive derivatives. All you get out of there is e to the x's. So the combination of the two are still going to give me a repetitive derivative. So a lot of times your textbook will give you a table on how to represent these, but if you're not sure, you can always take just a few minutes and go over to the side and start doing derivatives real quick. So if you have x squared e to the 2x, start doing derivatives real quick. So I'd have a 2x e to the 3x plus 2 x squared e to the 2x, right? That's just our product rule. And if I did it again, I would end up with product rule for both of these, 2 e to the 3x plus 6x e to the 3x plus product rule here, so that's going to be 4x e to the 2x plus 4x squared e to the 2x. Now, combining my like terms, I can combine these here in the middle. I'd have 2 e to the 3x, 10x e. How did it become a 3? It's not going to matter. That's a 4. Not that the number's not going to matter, don't worry. E to the 2x and 4x squared e to the 2x. So what did I end up with so far? I have just a number times an exponential, a number x times an exponential, and a number x squared times an exponential. Now think about it. From this piece, anytime I take the derivative of this, all I'm ever going to get out of it is a number and an exponential. If I take the derivative of this, I'm going to have to do the product rule. That's kind of like this. All I'm ever going to get out of that is a number, an exponential, and an x and an exponential. So that's always going to give me the same two pieces. And this is what we started with. And this, we know, is always going to give us what? X squared and an exponential, x and an exponential, or just the exponential. Which means you can think about it like this. The only things we're ever going to get out of this is, I'm just going to do it kind of the order we did there. A number times our exponential plus x times our exponential, or x squared times our exponential. So those are the only things that can possibly happen if we start taking our derivatives. Now, just for kind of some ease, it doesn't matter how you do this. You could also factor this out and you got a plus bx plus cx squared times e to the 2x. You could write it like that if you wanted to. Either one is fine. Now, a quick check. Do any of these pieces show up in our homogeneous solution? No, those are just sines and cosines. So we're going to have to take all the derivatives and plug it in here. So I'm going to do the derivative of the first one. It doesn't really matter. So yp prime can be 2a e to the 2x. That's this. Here I got to do the product rule. So that's b e to the 2x plus 2bx e to the 2x. And the product rule here with c's, that's 2cx e to the 2x plus 2cx squared e to the 2x. All right, very, very ugly. So yp double prime is going to be equal to, all right, I got to take the derivative of all of this again. Now, constant here, so this is just going to be 4a e to the 2x, 2b e to the 2x, product rule, and product rule here. So this is going to be 2b e to the 2x, 4bx e to the 2x, plus product rule here, that's going to be 2c e to the 2x plus 4cx e to the 2x. And we're bringing, let's go, we got room. And the last product rule is going to be 4cx e to the 2x plus 4cx squared e to the 2x. Ooh, what a mess. Okay, so we're going to plug it into our original differential equation. Now I'm going to start grouping things here a little bit differently. Let's take all of this, because this is our first term. I'm going to cheat here, so that's our y double prime, plus, again, I'm cheating, just because I don't feel like writing all of that again. I got to add 9 times our guess, so that's 9 times this guess up here. That's 9 times ae to the 2x, 9bx e to the 2x, 9cx squared e to the 2x. And I know all of that just has to be equal to, we'll put it over here. All of this has to be equal to x squared e to the 2x. All right, so on the right-hand side, we're going to have to combine things that are alike. So let's go x squared e to the 2x. So let's start with just constants times e to the 2x. So here's a constant, that's 4a. Here's a constant, 2b. Here's a constant, 2b. Here's a constant, 2c. And here's our last constant, 9a. Those are just e to the 2x's. All right, now let's take a look at x e to the 2x. Here I have 4b. Here I have 4c. Here I have another 4c. And here I have 9b. And those are x e to the 2x's. So now let's just look at how many x squared e to the 2x's I have. Now that would be this piece right here. That's 4c. And way over there, 9c x squared e to the 2x. All right, so is that all of them? Let's see. 4c and 9c. All right, so let's take a look at what we have here. Now, if we combine all of our like terms in here, we have x squared e to the 2x. I have 4a and 9a give me 13a plus 4b plus 2c e to the 2x. Plus, here I have 13b plus 8c x e to the 2x. And our last one here is just 13c x squared e to the 2x. All right, now I got to... Okay, now all I got to do is solve for a, b, and c, and we're going to end up with a kind of a system of equations here. So I do need a little bit more room, so I'm going to go this way. We just have to remember what our complementary solution were. Let's start with the easiest one first. Now we're just equating coefficient. Over here I have an x squared e to the x. Over here, what do I have in front of x squared e to the x? I have 13c. So from the very first equation, I can see 13c has to be equal to 1. Because that's what's in front of x squared e to the x on this side. That's what's in front of x squared e to the x on the other side. All right, here I have 13b plus 8c. Now that's what's in front of x e to the 2x. Now since I don't have any of those over there, that means that that has to be 0. Now all of this is what's in front of e to the 2x. Since I don't have any e to the 2x's on the other side, that also has to be equal to 0. So let me go ahead and, again, we're going to have to remember what that was. 13a plus 4b plus 2c has to also be equal to 0. All right, I'm going to get all this out of here so we can get back to where we kind of were. I said it was a bunch of algebra. I didn't say it was going to be quick. It's just a little bit of algebra. All right, so easy enough. We got a little bit to do here, but I can see that c is equal to 1/13. I plug that in over here. I know 13b plus 8/13 is equal to 0. So moving that over, I get 13b is equal to negative 8/13. Divide both sides by 13. So let's see, 13 13s, 9 3 3 1 9 6 1. So 169. All right, so now we know what A and B are, and I'm guessing this is going to be horrible. We plug those over here. So let's see, we got 13A plus, well, minus. B is negative 8 169. We plug that in there, that gives me negative 32 169 plus 2 13ths is equal to 0. Solve, and we get A is equal to something. Horrible number, I'm not doing that. So I'm just going to leave it there. We can figure that out in a second. So what do we have so far? We have our complementary solution, which was C1 cosine 3x plus C2 sine 3x. And our guess for our particular solution was A plus bx plus c x squared e to the, I'm going to say 2x. Guessing because I don't remember what I wrote. So now our particular solution, all we got to do is plug what A, B, and C are in here. So our complete solution is C1 cosine 3x plus C2 sine 3x plus whatever A was, plus what was B? Negative 8 over 169x plus 113x squared e to the 2x. All right, so there you go. Other than not knowing what A is, that horrible number. It's not that bad. You know your complete solution. So now if you have any arbitrary or any initial values, now you can plug it in and figure out what your arbitrary constants are. So as long as your non-homogeneous part has repetitive derivatives, you can always guess at the form of the answer, plug it in and find out what the constants have to be to make it work. Again, your book probably has a table to kind of show you what the normal guesses are. Might make it a little bit easier on you.